Hello. On behalf of Physics Today and Wiley, welcome to our webinar today. My name is Laura Federuso, and I'll be your moderator. Before we begin, I have a few housekeeping items that I would like to address. First, we strongly encourage audience engagement. Please feel free to introduce yourself in the attendee chat and engage with each other. If you have questions, please put them in the chat, and we will do our best to address them during the live Q&A at the conclusion of today's webinar. And lastly, if you are having issues with seeing the broadcast, please try to refresh your web page or clear your cookies. We recommend using Google Chrome as your browser for the broadcast. Now, it is my pleasure to introduce our speaker for today, Linus Anderson, for their presentation titled Equation-Based Modeling with COMSOL Multiphysics. Thank you.
Thank you so much, Laura. Hi, everyone. Welcome once more to this webinar on equation-based modeling. This is usually a very popular topic. Today is not an exception. What a crowd we have. Thank you so much for joining in. You know, I'm in Stockholm, Sweden, hence my accent. It's 8 p.m., but I don't mind because I get to stay up and talk equation-based modeling with you and also demo a little bit of equation-based modeling. So let's get right to it. So I'm going to set the stage for what we will be talking about today. First of all, COMSOL Multiphysics is a tool for multiphysics modeling. But fundamentally, when you're modeling physics, what you're really doing is you're finding numerical solutions to equations. In a heat transfer problem, you may be solving the Poisson's equation for the temperature. In an acoustics problem, you could be solving a Helmholtz equation for the acoustic pressure, and so on. But when you're using our physics interfaces to do that, you don't necessarily need to think in terms of equations. The GUI has you enter physical properties and conditions. You specify heat fluxes and sound sources and the like. Now, with the mathematics interfaces, which is what we'll be focusing on today, you skip past the physics and you get straight to the equations. You choose which equations you want to use. You combine them to get systems of equations. You enter mathematical boundary conditions and initial values. If you have a model that's based mainly on physics interfaces, you can use equation-based modeling to add functionality, such as control mechanisms or constraints to it. And if you like, you can also use only the mathematics interfaces to set up and solve a system of equations from scratch. In slightly more detail, COMSOL Multiphysics has a unified interface for defining a mathematical model from your input, for turning that into a numerical model, for solving that model, and for displaying the results. Again, our physics interfaces are tailored for letting you define problems in various fields of physics. These can be mixed and matched freely. You can also combine them with the mathematics interfaces. You could, use a mathematics interface to set up your own equation for how some sound source is changing with time, maybe. And you can couple that to an acoustics interface, that is a physics interface, to model the resulting sound pressure level in a room. Now, the mathematical model equations are the system of PDEs, ODEs, and so forth that you get from the physics and mathematics interfaces in your model. What makes COMSOL so unique is that it's not until you've specified all these equations that they're assembled into a set of numerical model equations, those large matrix equations that you'll be solving with typically the finite element method, but also boundary elements and other methods. This makes the software very general. You don't have to rely on any custom subroutines or iteration schemes to bring it all together, and there are no limits to how you can couple your equations. Being a multiphysics software, we offer a lot of different physics interfaces that let you model a wide range of physics. So why then might you want to use a mathematics interface? Well, one reason would be to extend the functionality of the physics interfaces. You can add contributions that aren't already there in the equations, perhaps implement an advanced constraint. Say you're modeling structural mechanics, and instead of setting a displacement with a fixed value as a boundary condition, you want to solve a separate equation on the boundary to find and stipulate a local displacement, maybe. Then we have control systems. In the application library that comes with the software, you will find an example model of a PID regulator, adjusting the inlet velocity of a gas into a reactor to reach a desired gas composition at a point of measurement. But you can also set up your own equations from scratch. Those can be equations describing physics that we don't yet have an interface for, or a problem that isn't even physics related. So Black-Scholes for stock options, models for spread of diseases or forest fires or memes even, traffic flow. If you can think of a partial differential equation, chances are you can set it up and solve it with COMSOL. For today's demo a little further on, I intend to set up an equation describing how the concentration of mosquitoes evolves over space and time inside my little cabin in the woods. In fact, out of the full hour that we have today, I plan to spend at least half of the time on that demo. And for those of you who didn't specifically join in to learn about mosquito modeling, don't worry, I'll keep it very general and hopefully useful to everyone. Uh, it's clear that you all have vastly different things that you want to model, but luckily the process of setting up and solving a model is very similar regardless of what equations you're solving. Let's now first have a look at the tools that we have for equation-based modeling. On the left of this slide, you'll see a list of our mathematics interfaces. The most important ones are the PDE interfaces, partial differential equation interfaces. The ODE and DIE interfaces contain some subsets of the same functionality, and the classical PDEs are similar to the PDE interfaces, but with some commonly used equations already in place. Chief among the PD interfaces are the coefficient and general form interfaces. These are rather similar. You can typically choose which one you prefer. The coefficient form has more, well, coefficients, but you can add those to the general form too if you like. So what you do when you set up an equation is basically you pick one of the interfaces, you fill in values, parameters, or expressions for the various coefficients. Suppose you use the coefficient form and you want to set up the standard heat equation. So du dt equals some factor times Laplace of u. Well, what you do is then you simply locate the coefficients. The coefficient before du dt is dA, so you provide a value for that. And then the Laplace operator, that's the divergence of a gradient, so you enter a value for that as well. As you can see on the right, the various coefficients are named after what they usually represent in a physical equation. So dA is the damping or mass coefficient, C is the diffusion coefficient. For the heat equation, you may also want to enter a source term F. If you look closely at the interface for the coefficient form, or to an even greater degree the general form, it may seem just a little bit limited. I mean, surely there are lots of equations that can't be expressed on these forms, right? The general form has just 3 coefficients to fill in. I guess you can't do much with that. Well, the thing is, anywhere you can type in a number, you can also type in expressions. And expressions can be quite arbitrary functions of space, time, and the solution variables themselves. So for example, if you're solving for a variable u, your source term f can well read something like du dx plus sine of u plus the integral of u over some boundary in your model, non-local coupling that is. And you can be, I mean, only your imagination sets the limits really. On the right on this slide, we have entered coefficients for the Black-Scholes equation in 1D, and you can see that some of them involve the x coordinate. And when that is the case, you just type in x. With the interfaces come options for setting up boundary conditions. This slide looks way more complicated than it typically is to do this. Let's just focus on the settings window on the right. This shows you how you set up a Dirichlet condition, u equals 0. To do that, you simply pick Dirichlet from a list of conditions, you select prescribed value of u, and you enter the value you want to use, be it 0 or some other value. Similarly, for a Neumann condition, you enter a boundary flux and an optional boundary absorption term. A walkthrough of the PDE interfaces wouldn't be complete without mentioning the weak form PDE interface. And don't worry, this is by far the scariest slide in the entire presentation. It does get easier from here. Basically, the weak form is an integral form of the equations. You can get it from the general form by first multiplying with an arbitrary test function u hat and then integrating over the domain. You integrate by parts and then you arrive at the final expressions. The weak form is the more native formulation that our physics interfaces tend to use. It helps to be acquainted with it if you want to try modifying the equations that those interfaces are made up of. But if you just want to set up your own equations, the general and coefficient form interfaces tend to be easier to use. On that note, the coefficient form is preferable if you have an equation with coefficients that correspond to physical properties. You just fill them in and you're done. The general form has fewer coefficients, less clutter, and is good for conservation laws, for example. This slide says the weak form facilitates certain formulations. That is true, provided, of course, that you learn how to use it. To that end, if you go to comsol.com/blogs, you will find a number of articles dedicated to the nuts and bolts of weak form modeling, and I won't talk much more about weak form in this presentation. In addition to the FEM interfaces, we have a waveform PDE interface that uses the discontinuous Galerkin method for efficient time stepping. And there's a PDE interface that uses the boundary element method, which can be a useful option in geometries with, so to speak, more volume than surface, so large empty spaces between relatively small objects. All right, it's time to get practical. Let's see if we can use some equation-based modeling to solve a problem. What you see in this image is me lying in my bed at night in my cabin. Unfortunately, I've left the window open and the cabin has been invaded by mosquitoes, represented by the black dots. The mosquitoes are making their way towards me. A few of them have already landed on my foot. One has landed in my face. Now, on the shelf on the wall above me is a mosquito trap. This trap emits a scent that attracts the mosquitoes. What I'd like to find out from this model is how effective is the trap? More precisely, what percentage of the mosquitoes reach the trap versus how many reach me? And to find out, we need first come up with an equation that describes mosquito flight. If we first disregard anything that will attract the mosquitoes, and we also neglect wind, which is probably a good approximation inside the cabin at least, I posit that those mosquitoes will be flying around aimlessly. It's what you might call a random flight or a three-dimensional random walk. That's the first equation on this slide. X naught of t equals the sum of small random steps. I'm not a mosquito expert, but I don't think this is incredibly far from the truth. You may be familiar with random walk presented as a drunken person trying to make their way home. But it turns out that the mathematician who first came up with the equation was in fact inspired by mosquitoes when he thought of it. Unless that's apocryphal, I'm not completely sure, but that's what they say at least. The random flight is a good start, but it's not a complete model. If you've ever studied mosquitoes, you will have found out that they're well drawn to the observer, unfortunately. They sense your smell, they sense the carbon dioxide that you're breathing out, perhaps they even sense your body heat if you're close. To make it easy, I will lump up all those effects, everything that's appealing to a mosquito, and I'll do that into an attractor concentration, Ca. We'll then add a velocity component that's proportional to the gradient of that concentration. That's the second equation on this slide. So physically speaking, what this expression is saying is that on top of the random movements, the mosquitoes will attempt to fly in the direction of increased attractor concentration. And the steeper the concentration increase, the greater the velocity. This, of course, is a bit of an approximation. We should probably, for example, impose a limit to the flight speed that the mosquito can reach. We don't want to model supersonic mosquitoes. But for a first rough model, I think it will work just fine. You can see on the illustration here what a typical flight pattern might look like in a situation with the concentration increasing in the direction of the arrow. Now, neglecting again any wind inside the cabin, we should be able to model the local attractor concentration everywhere using a diffusion equation. For simplicity, let's absorb the constant k in front of the concentration gradient to make it an equation for a velocity potential. That is, the non-random part of the velocity of the mosquito is going to equal, not just be proportional to, the gradient of this velocity potential. The equation that we end up with is one of the most basic PDEs there are. It's called the Laplace equation, and I just love it because it's so easy to deal with and it solves so quickly. So there's a reason why I'm using this as a demo. Now it says on the trap that I bought that it's 60% more attractive than human skin. I'll conveniently take that to mean that it's got a velocity potential that's 60% greater than mine. I've basically invented some numbers that we'll use. So 0.5 meters squared per second on my skin and 60% greater, that's going to be 0.8 meters squared per second on the trap. To get the model started, let's now switch over to COMSOL to set up and solve this equation for the velocity potential. So here's COMSOL, a mostly gray window, but that's soon about to change. The first thing we're going to do is walk through the model wizard, in which you're making a couple of choices that will lay the foundation to your model. So space dimension, well, it's going to be 3D, of course. Note that we have planar as well as rotationally symmetric 2D, 1D, and also 0D. 0 dimensions would be for models with, well, for example, if you have chemical reactions in a perfectly mixed tank, or anything else that doesn't depend on any of the spatial coordinates, that's going to be 0D. Now, we're picking 3D for this model. Choice of physics. This is where you would, for example, pick your heat transfer or acoustics or semiconductor equations. We are going to go to mathematics and browse down to classical PDEs, Laplace equation, and I'll add that to the model. For the dependent variable, it's a velocity potential. I'm calling that capital V. And we get to specify the units it's going to have. And that's going to be meters squared per second. Remember, it's a potential for velocities, and velocities have units of meters per second. So the potential will have meters squared per second. Final step in the model wizard is to select the study. And I'm going to go for a stationary study. This brings us now to the model builder, which is where you're spending most of the time setting up your model. You could conceivably do it also almost exclusively in the ribbon tab here on top, but I tend to right-click my way through the model builder. And the first thing we're going to do here is bring up a geometry. So if I right-click on that, we have our built-in CAD tools. You can draw a bunch of primitives and so forth, but I'm going to be a little quick and just import a CAD file that I prepared already. And we do support most common CAD formats. So it looks like this. I'm going to click wireframe rendering to have a better look inside. And that's the geometry. If we zoom in a little bit, you can see me in my bed. Over to the Laplace equation. So first thing to do is decide where to solve it. Per default, it's going to be active everywhere, including in the walls, but I'm going to select only the air domain. So that's the big air volume here and also the window. Going over to Laplace equation, we can see what equation we are solving. The divergence of the negative of the gradient of the velocity potential equals 0. So that's the Laplace equation. And this is normally where you would also enter values or expressions for any of the coefficients in the equation. Only for the Laplace equation, there are no coefficients, so there is nothing more to do here. We do need boundary conditions, and the first one we'll apply is a Dirichlet boundary condition over at the window. The equation is right here. It says V equals R and R equals 0. So V equals 0. Simple as that. And this tells us basically, or we're stipulating right now, that the concentration of the mosquito attracting chemical or whatever it might be, the attractor, is 0 at the window. So next, there's a boundary condition. I'm going to apply that to my skin. So I can use maybe an XY plane to easier select that, and select box tool like that. So this is one part of my body that sticks out of the blanket, and here's a very unfortunate little foot. It's going to hurt once we've solved this model. Right here, we're prescribing a different value of the attractor, 0.5. And one more Dirichlet boundary condition. Oh yeah, before we even do that, notice it took me a couple of seconds to select these boundaries. We might as well create a selection out of that so that we can reuse the same selection at any time if we like. I'm calling that selection skin. Now for the second Dirichlet condition, we are applying that on the trap this time. So different potential, 0.8, and we will name that selection the trap. That is basically all we need for setting up the Laplace equation. But before solving, we'll also need a finite element mesh. We can get that by just building the default mesh. It's called normal. It's really pretty coarse, but that's okay because I'm not looking for a really accurate solution. We just want it to be solved relatively quickly. And this is what the mesh looks like inside. We can see the mesh on the surfaces, but it's really a volumetric mesh. Solving is done from here. I'll just hit compute, and I foresee this won't take more than a second or two. And indeed, we have the solution. Did I tell you that the Laplace equation is easy to solve? It really is. So we get the solution plotted on 5 equidistant slices throughout the geometry. We can go with maybe 1 slice instead for clarity. And if you look at the scale here, it goes from 0 up to 0.55 or something like that. We did apply 0.8 on the trap, but the slice doesn't quite touch the trap right now. So let's move it there to be sure that we really do have the right solution. And indeed, it does go up to 0.8 right now. So it's all well and good. One more neat plot that we may want to look at is a streamline plot. So per default, streamlines will they will run from a boundary that you select, why not from the window, and they will follow the gradient of the solution. So the gradient of the velocity potential, that is the velocity field. The gradient is written as Vx, Vy, Vz. So that's short for dV dx, dV dy, dV dz. If I click plot now, I've got streamlines, and those streamlines will end up either on my skin or at the trap. And these streamlines actually now represent the paths that the mosquitoes would follow had they not been dealing with this random walk. If they were just completely just following the attractor, following the scent, they would follow those streamlines. So we could, right now, if we wanted to, we could just count the number of streamlines that end up on the trap and the number that end up on me, and that would give us an idea of the accuracy, or not of the accuracy, but of the efficacy of the trap, I should say. But that's, of course, not quite good enough for us. So let's take just a little bit, let's take this just a little bit further. So we've modeled now the velocity potential distribution, right? It's now fairly easy to use that in a particle tracing simulation, which follows individual mosquitoes as they fly across the room. You can use a Brownian motion feature for the random flight, and then you can add the contribution from the velocity potential. If you do this for many mosquitoes, counting the number of mosquitoes reaching the trap and reaching my skin as you go, you will get a measure of the effectiveness of the trap. So let's go ahead and do this. Going back to the model, we have the velocity potential already. Let's add particle tracing. So I'll right-click on this component 1 and I'll select Add Physics. And this time, why don't we just search for particle tracing to see what physical interfaces we can choose from. So this gives us 3 different particle tracing interfaces. I think we can exclude charged particle tracing because these mosquitoes do not carry any significant amount of electric charge. It would seem natural perhaps to go with the mathematical particle tracing interface, but I suspect, especially granted the limited time we have on offer today, that particle tracing for fluid flow would be a better option. Because the thing is, I happen to know that this interface has the 2 forces that we need to apply already available. It's a Brownian force and it's a drag force, which mathematically is the same as the advective force from the attractor. So this time we will be using a physics interface, but we'll tweak it so that it works for a situation that is distinct from what it's mainly intended for. And there is no shame in that. Instead, you should be proud if you do that because you're not unnecessarily reinventing the wheel. So just like with the Laplace equation, with the particle tracing equation now, we are starting out by defining which domains it should reside in, where we want to solve this equation. And then there are a bunch of things to fill in, and we will need quite a number of parameter values to do that. So I prepared some parameters for us. I will just open a file of parameters. Normally you would type these in and just tell the software what values you want to use, but I prepared them in advance. So among these parameters, you will find a mosquito mass and a mosquito radius, if you will. So we're modeling particles, remember, they're point-shaped, so you can look at them as really tiny spheres, if you like. If you approximate well enough, anything is going to be a tiny sphere. So particle tracing for fluid flow, first thing to fill in is the particle properties, and we're going to specify the mass and diameter. So particle mass is one of the parameters that we have. That's the mosquito mass, and we have the particle diameter. That's twice the mosquito radius. Okay, next up, we want the mosquitoes to come in through the window. And for that, I'm going to use an inlet condition. We'll apply that over here. I'm going to go for density of mosquitoes with quite a high number of particles per release. It's going to be NM equals 1,000. That's how many mosquitoes we're modeling. Obviously, the more mosquitoes, the better the statistics, but also the longer the solution time. So I'm going to go for 1,000 mosquitoes. As the mosquitoes enter the window, they will be traveling at some velocity, and I'll have them start out at the advective velocity, which, as we have seen, is equal to the velocity potential gradient. Now, watch closely. This is where we enter the velocity, and we have solved for the velocity potential. It's called capital V, and you may have noticed on the streamline plot over here that the gradient is called Vx, Vy, Vz. So all we need to do now to couple these two equations together to get the inlet velocity of the mosquitoes from the advective velocity that we solved for is to enter these same variable names. Vx, Vy, Vz. That's how you couple equations together with COMSOL. So in order to have, let's see, a density, we need a density as well, and that's going to be proportional to the absolute value of Vy. Basically, the greater the advective gradient, the greater the flux of mosquitoes. And you can really enter any type of expressions here as well. That's the inlet. We also need some outlets. And outlets in this case are places where the mosquitoes don't travel any further where they reach them. So it's obviously going to be my skin. And this is where the selection is useful to have. So as the mosquitoes reach me, they will freeze. They will not fly any further. And we will also add a counter to count the number that reach these boundaries. And that's called an accumulator. We can set the type to count. We will enter a name for it. Let's call it skin. And the source is 1. This way, each time a particle reaches my skin or a mosquito reaches my skin, we're adding 1 to the counter. And I'm going to do the same. I'll actually duplicate this outlet, and I'll move it to the trap. And I'll use a separate counter on the trap. So let's call that trap. We also need some forces to affect the mosquitoes. And we want, first of all, the Brownian force. So forces, Brownian force, this is the random walk thing, right? So we'll apply that to all domains, and we need a temperature for that. Let me actually, in fact, start out with the advective force. Sorry about that. So the advective force is really the same as a drag force. In fluid mechanics, we use drag forces all the time for fluid particle tracing. And the equation, which you can see right here, looks like this. It features 2 different velocities. It's u for the fluid velocity and v for the particle velocity. And the force will act to try to make those the same. So the particles will propagate with a velocity that's similar to the fluid velocity. And once again, our fluid, so to speak, is this attractor gradient. This is what gives us the advective component. So I'll just fill that in again. Vx, Vy, Vz, like that. Then the constants over here are the properties of the mosquitoes and also some properties of the background flow, so to speak. And those are dynamic viscosity and density. We can create a material for that. So a blank material, and I'll just enter the parameter values that I prepared for those, like that. And that's our drag force. Now let's go for the Brownian force as well. So this time, applying that everywhere, we have an equation that looks like this. This gives us, for molecules in the air, it gives them their random thermal motions. That's why I fill in the temperature. Turns out that if you define a random walk standard deviation, so a typical step length for the random walk, that actually translates to an equivalent temperature, which you can just type in. So equivalent temperature like that. That is all we need for the particle tracing. And I could go on now and set up a time-dependent study for solving it, but let's not, because it will take approximately 5 minutes to solve that equation. We don't quite have that time. So instead, I'll just open up a solved version of that model. And it's really the same model that I'm opening up right now, with the exception that I've used a slightly finer mesh, and I've also worked a little bit on the plot. So this is the geometry, looking slightly nicer than before, although it's the same geometry, of course. We have the velocity potential distribution just plotted differently. You can do lots of cool plots with COMSOL. And we now also have the resulting particle trajectories. So this is a snapshot of the situation in the room after 30 seconds right now. I can click forward in time. You can see this little red dot. That's just one of the mosquitoes, and I chose to color it and also add a little path behind it, so that as I click forward, you can see that it's getting sort of dangerously close to my foot. But if we fast forward a little bit to the end of the simulation, you can see that it actually doesn't reach my foot. It reaches the trap instead. And it shares that same fate with a lot of other unfortunate mosquitoes, although a fair few got lucky as well and got to my foot or my head. So how many arrived at each destination? Well, let's find out. We're going to plot that because remember we have the counters that we set up. So we can now search for them. I called one of them skin. So we have a couple of variables associated with that. We want the sum of this accumulated variable. You can plot it like this, just raw. This gives us the number of mosquitoes versus time that have arrived on my skin. If we divide that by the number of incident mosquitoes, 1,000, we should get a fraction. So the fraction of mosquitoes that come to my skin by the end of the simulation. And likewise, we can search for trap and find the same fraction, but for the trap instead. If we plot that, we will have learned that, no, we will not have learned that undefined variable. It's not NP, it's NM for mosquitoes, not number of particles. Sorry about that. So I sometimes do get these really helpful error messages, even though I've been modeling for 20 years with COMSOL. It happens to all of us. So trap, 55% of the mosquitoes, and some 45% of the mosquitoes go to my skin. So it's not any kind of marvelously good trap by any means, but it still does help a little bit. What about the accuracy of this model? Is it any accurate at all? No, it's not, because I personally decided which equations to use. I made up the parameter values, and I'm not a mosquito scientist. But that aside, if we're talking about the purely mathematical error sources here, there's first of all going to be a small numerical error in the velocity potential because of the mesh. And that error is quite controllable. We can just refine the mesh a little bit and see how the results change. Spoiler, not much. The mesh is fine enough already. But there will also be a statistical error because I'm using a limited number of mosquitoes. This error is in fact quite clearly visible on these plots, in these little wiggles that you get. For a higher number of mosquitoes, we should expect the curves to be a lot smoother and the end result perhaps slightly different. Okay, so we could consider running the model with maybe 1 million mosquitoes instead, but I think we can do better than that. Let's have a look at the slides again for a second. So if you'd like to picture now, I'd like you to picture now not 1,000 or 1 million mosquitoes for that matter, but rather a continuous mosquito cloud. Just too many mosquitoes to count. That can be scary, I know. So if you prefer, think of an evolving probability density cloud instead. The local concentration then represents the chances that you'll find a mosquito in a certain position at a certain time. Those two descriptions are actually equivalent provided you neglect any mutual interaction between the mosquitoes. The continuum equation that you'll end up with here, and this is derived straight from the discrete equation that we used so far, is the convection-diffusion equation. It has a diffusion coefficient that you can get from the parameters of the random walk. Then there's the advective part with the gradient of the local velocity potential from the previous simulation. In this continuum model, we are going to send in a concentration pulse, and we will see how it eventually distributes between the trap and my skin. The boundary flux will be available from the solution. We can create a global equation to integrate that over time. So if we succeed, we are going to end up with results that resemble what we get from the particle tracing, but here's a different way of doing that and avoiding the statistical error by setting up a continuum equation. So we will add a third interface, third physics interface to this model. And this time, it would perhaps be tempting to go to mathematics and find classical PDEs, convection-diffusion equation. But again, mostly for lack of time, I'm actually going to go to a physics interface called transport of diluted species. So this is the same equation. It's almost the same experience. It's just got a collection of slightly more advanced boundary conditions that we can choose from. So it's going to be just a little bit more convenient to use that interface. So you know the drill by now. It's going to be active in those two domains. And if you go down to the equation here, this is what it looks like. So if you look at the equation here, it first sets the divergence of J, and J is minus D times the concentration gradient. So the first term corresponds to diffusion. And the second term is a velocity field, scalarly multiplied by the gradient of the concentration. As you know by now, the velocity is the advection. So we'll want to fill in the velocities from the velocity potential solution, like that. And then we've got the diffusion coefficient, and that I have as a parameter. It so happens that it equals, again, the random walk, this time squared and divided by 6. Why 6, you may ask? That's an unusual number to divide by. Well, it's really 2 multiplied by the dimension. So this is for a random walk in 3 dimensions. It would have been divided by 4 if it were a random walk in 2 dimensions, etc. So D it is, and we'll type that in right here. And this needs, of course, that's what we've done with the parameters, be adapted so that it corresponds to the same kind of random walk as we've done with the particle tracing. Hence the formula with sigma squared divided by 6. So random walk really is diffusion in a sense. For boundary conditions, we will need our inflow of mosquitoes at the window again. And since this is a continuous equation now, we cannot, as we did in particle tracing, have them all enter at time equals 0. That would be like a perfect delta pulse, and that's not going to be possible. But we can go for a very short pulse in time. So I can enter any kind of expression in terms of t here, like t squared times sine t, whatever I like. But I also have the option to, for simplicity, define a function over here. So I can go for a rectangle function with some smoothing. Let's have a look like this. If I plot that, yeah, that's a good pulse. It will take a second then for most of the mosquitoes to enter the model. This pulse is now called rect1 per default, and that means I can just enter rect1 here of t. This is how we're sending in the mosquitoes. On the skin and on the trap, I'm going to use an open boundary condition. So I'll select the skin for that. And this is the exact reason that I'm using the transport of diluted species interface rather than the equation-based one, because it has an equation that's slightly more complicated than what we have the time for. It really, what it does is that it works as an outlet, but it's also, sorry, preventing any mosquitoes from ever coming back through the boundary and into the model again. So to make the simulation equivalent to the particle tracing, we need this condition. So 1 on the skin, and then we'll also put 1 on the trap. All right, I believe I mentioned a global equation as well to integrate the flow of mosquitoes over time. I'm not sure that time permits actually, so with your permission, I'll just skip that and open the solved version of the model once again. And that's going to be this one. It's not this one. That is the one I had already. It's just cabin, featuring everything. So here's now, in a second, right here, the convection diffusion solution. We're looking at the mosquito density at time equals 30 seconds. And this is to be compared with the particle tracing solution, which at time equals 30 looks like this. So if you sort of squint your eyes, you can see that you have a greater concentration of mosquitoes in this area than elsewhere. Not too many have gone over here, for example. And you see kind of the same overall picture in the convection diffusion plot. So at least they're qualitatively similar. But more interestingly, here's again the plot of fraction of landed mosquitoes per destination, and so far only from the particle tracing. But I prepared one from the convection diffusion as well. So let's just enable that and compare. For the final reveal now, they do end up pretty similar. They're not exactly the same, but they're close enough. We are aware that there is, of course, a statistical error here in the particle tracing simulation. Now, here again are those results from the models. I believe I might have used a slightly finer mesh in creating these images, so they might be just slightly more similar than what they showed up. And the solution time is fairly similar between the particle tracing and the convection diffusion model. It's some 5, not more than 10 minutes in each case, at least if you're solving for 1,000 mosquitoes. You will see that the convection diffusion results are clearly smoother, and that's because they don't have the statistical error that you'll get with particle tracing. As for systematic differences in the results between the two approaches, there really aren't any, because this is what you get if you use 50,000 mosquitoes in the particle tracing simulation. It takes a bit longer to solve, but in the end you end up with a practically perfect approximation of the convection diffusion equation. Isn't mathematics beautiful? I'll hasten to add that 50,000 mosquitoes in a single cabin is more than I'd usually expect to get, even in peak mosquito season in a typical Swedish forest. Now, to wrap up, the mosquito flight simulation that we've been looking at is, of course, just one of virtually endless phenomena that you can model with equation-based modeling. In this example, we started out from scratch with the equation-based interfaces. You can also extend the models based on the physics interfaces with additional equation terms, with ODEs and with PDEs. I'll be happy to expand on all this and more during the Q&A, which I believe it is now time for. Do we have any questions already?
Thank you so much, Linus, for the presentation. Yeah, we have quite a few questions, so we can jump into those. Our first question is, I have been simulating a microfluidics model with creeping flow level set method. It hasn't worked properly for me, I think due to the abstraction between the different sizes within the geometry. I have a 100 micrometer wide microchannel, which feeds into a 2.3 millimeter radius well. Is there a way to fix it?
Well, the aspect ratio between 100 microns and 2.3 millimeters doesn't sound that, it doesn't sound too challenging to me. Had there been a number of orders of magnitude in between, I would have suggested some kind of multi-scale model to deal with that, because you can definitely zoom in and model one small part of your geometry and then combine that with a less detailed overall geometry and do lots of stuff like that. But in this case, I doubt that this alone would be the main issue, unless I misheard. But you're talking 100 microns and a couple of millimeters. Yeah, that should be fine. What I would do is contact our beautiful support department. I'm actually one of the people working in it, and I can vouch for the quality of their help. So just get in touch and ask for support, and we will try to help you out.
Great, thank you. We have another question. Can you specify a source term in only one part of the system domain?
Yes, for sure. There are two things you may mean by system domain here. In COMSOL, we have a terminology wherein a domain is already a separated part of the model. So if you draw some dividers in different places, you will get different domains. And then you select just one of those domains, and you can set up your source term in that domain. But suppose you want the source term to exist in just part of that domain. You don't have a physical divider, but you want the source term to be 0 in some parts and non-zero in other parts. Well, then what you do is you just type in an expression in terms of your coordinates. So you could, for example, if you wanted to be in a sphere, you could type in your source term, 5 watts per meter square, Kelvin, whatever it might be, multiplied by square root of x squared plus y squared plus z squared less than 1, for example. Then that comparison less than will give you 1 if it's true, and it will give you 0 if it's false. So that way you can have your source term reside only in the part of your domain that's inside this particular sphere. If you have a more complicated shape that you want to have your source term to be non-zero in, you can use interpolation functions from imported data from text files, for example, describing where you want the source term to be. Or for that matter, any material properties. They can also vary freely with your coordinates.
Great, thank you. Another question, how do you validate errors in your solutions?
Oh, that's a huge question. I could probably do a whole webinar on that one alone. But there are different types of errors. I mean, there are systematic errors clearly in taking reality and just turning that into a model. And most of those errors are errors that you're willingly making because all the equations that we're solving are ultimately approximations of reality. You're neglecting maybe wind, as I did with the mosquitoes. You're neglecting other things. So that's the part of the system, or the error rather, that your engineering skills are really useful to characterize. But I assume you may be talking about the purely numerical error here. So that is, I mean, given these equations and boundary conditions and what have you, what kind of numerical error do you have and how do you characterize that error? So what we tend to do is we run a convergence study over consecutive mesh refinements. So you can start out with a coarse mesh and you make it gradually slightly finer and finer, and you monitor how some output of interest is changing. You're not necessarily, for example, interested in the solution being optimally accurate everywhere in the model. It could be that you're looking for some particular output and you want that to be accurate enough or as accurate as possible. Then you can trace that towards versus the mesh density. Or you can even use an adaptive mesh to make the software automatically adapt the mesh such that it maximizes the accuracy of what you're interested in. Validation is also it also could be interpreted as how you compare the results with, I guess, known benchmark to make sure that there are no bugs in the software or anything like that. And we do have quite a lot of such benchmark models included in the application library that comes with our software. Those things we take extremely seriously. So you will be hard pressed to find computational errors in our products. So given a sufficiently fine mesh, your results can be arbitrarily accurate. That's the short story.
Okay, thank you. Another question, how do you ensure that dependent variables are positive in the simulation? And specifically, they followed up and said they don't want to use the segregated solver because their system is coupled.
Okay, that's quite a technical question. I do believe the reason they're mentioning the segregated solver could be that when you're solving heat transfer, we have a default thing that will, for each segregated step, turn on some kind of condition that makes the temperature positive everywhere. I'm not sure actually how those details work. I tend to be more into acoustics and electromagnetics myself, but I digress. We don't necessarily always ensure that variables stay positive because if they do turn out slightly negative somewhere in the model, that's just another numerical error, just like any other errors. I mean, suppose that we know that maybe a concentration, for a better example, must be positive. You cannot have a negative concentration anywhere. But if you have it